This is just going to be an example of a very nice continuity problem that may show up on your homework or on the AP exam or on your test or, again, just life in general, just throwing continuity problems everywhere there. The question is this. Here is a function. Notice that it is a piecewise function. We have two different functions and two different domains. And the question is, for what value of, there it is, a, for what value of a, what value of a makes this function continuous at x equals 2. And the way we're going to do this is there's a couple ways. The first way is pretty much algebraic and really, really easy. These problems should be easy. To make this function continuous at 2, we plug in 2 into each part of the equation and set them equal to each other. Great. So the first thing we're going to do is we're going to do 2 cubed, and we're going to set this equal to a times 2 squared. Great. 2 cubed is 8. 2 squared is 4, so a equals 2. Beautiful. And that's our answer. A is 2, and when a is equal to 2, that makes this function completely continuous on the entire real number line. Here's a graphical approach of what we just did. At 2, x cubed is hanging up here around 8, like that. And so the cubic graph looks like this for x less than or equal to 2. It is a solid dot because it is less than or equal to. And then y equals ax squared has a graph that is a parabola, but the shape of the parabola changes depending upon what a is. If a is 1, for example, then what we would do is we would, at x equals 2, the y value would be 4, and we're only graphing that part of the parabola. So this would be for a equals 1. Okay. Obviously that doesn't work because the whole does not match up with where the point is. So we need to scale this by a factor of 2, and the way to do that is to make a equal to 2. We plug in 2. 2 squared is 4, multiply that by our a equals 2, and then we get that, and then the parabola looks something like that. So this is just a type of problem that shows up. I do want to notice one thing, or point out one thing here, and that is this. If we zoom in on this picture, we get something that looks like this. There is our cubic graph in blue, and then our parabola in red sort of came off and looked something like that. And if we kept zooming in, chances are that this junction at this point, which was 2, 8, that this junction is probably not smooth. We talked about that before with our whole zooming in activity. And we'll talk later about what happens if this junction is smooth and how we get that junction to be smooth. It's going to be a fun, it's a cool thing to look at, so we'll look at that later. Extra information, not needed now. Goodbye.